In XRF spectroscopy, the element with the lowest atomic number Z that we can detect is sodium 11. We have sodium over here, so we see 11, the atomic number. Before sodium there are some elements of interest for art examination, and generally this one, like basically nitrogen, carbon, we can't tell them with our system. These are elements then we can map using the scanning electron microscope. Sodium is borderline actually. With my system that we are using for the course, I can't detect sodium. So I tried with different setup and filters, but as it is, I can't reach to sodium. This one is one of the thousands of XRF lines tables that you can find on the internet from different producers of XRF systems. So what we see is that in general they start from sodium. The first page of those tables start with sodium 11 over here. So we see here the peaks of sodium that are at 1 keV, basically. There is a K alpha 1, K alpha 2, and then there is the K beta. Those are close to each other, so basically the peak will be just one detectable and will be at 1 keV. Can we detect this low energy sodium peak at 1 keV using our system? Basically we can't. The problem is air. So you see, this is a close-up photo of our system. So this one is the X-ray tube, and this one over here is the spectrometer that is collecting the diffused X-rays from the target that will be positioned over here. Over here I put a ruler just to have an idea of the distance. And we see that the distance from the detector to the target is about even more than 1 centimeter, so 10 millimeters. Air, oxygen, nitrogen that are here can actually stop the X-rays, and this effect becomes more apparent for low energy X-rays. There are tools online to calculate the path of X-rays through air. So here I just put one that is very nice because it's very simple, so not that much input to give to this tool. So this is the website, the link over here, and this is the web page. This is the window where we have to input our parameter. So first of all, we can choose here the target material. So in this case, the idea is the target is air, normal air at normal pressure, atmospheric pressure. We have a drop-down menu. From here we can select air. Over here we can select the energy of the X-rays. So in this case we are looking for sodium, and we know from the previous table that the energy is 1 keV, and we input 1. Over here we have the target length. What's the thickness of this air that X-ray have to go through, to penetrate, to reach the detector? So we saw from our picture that it is about 10 millimeters, 1 centimeter. So we go here and we input 10 millimeter. The pressure we can leave 1 atmosphere over here. We click calculate and we get our answers. These are the results. So we see that the attenuation is given in percentage, and it is 98.7%. So we have just a transmission of 1.3%. Most of the X-rays are stopped. just 1/100 can go through and reach the detector. These values means that since we have the noise, we have also the beryllium windows that is interacting and stopping part of them, the beryllium windows of the detector, that we don't have any of the X-rays from sodium that can reach a system like ours, where we have this air gap. Maybe there could be some other system that are more specialized, that can detect a little bit of the sodium, but definitely for our system this is the border line. Of course we can see sodium then with systems where we can have like vacuum, like in the scanning electron microscope, where we have the probe for X-rays. In that case we don't have air, so we can better detect sodium and the other elements even below sodium. We can remove air with what's called an helium purge, so we blow helium on it, but that will be a little bit cumbersome to bring the tank with helium, so it's not something that is really practical for our application, just for art examination, and also just to see sodium. We have all the other elements that we can see, so we leave sodium to the analysis under the scanning electron microscope. After sodium, the next one is magnesium Mg. What's the energy of magnesium? So we go here in our table, we see magnesium is just below sodium, so it's the next one, and in this case the energy of the K alpha is 1.25, a little bit more, but in this case this 0.25 more keV added are enough so that actually magnesium is an element that we can detect, and we will see in the lesson about magnesium. Let's check it out with the software to see actually how much of the magnesium is expected to go through. There it is, so this is our software to calculate this path. So target material we can leave air, of course, then X-ray energy we want to input 1.25, and then we can leave everything as it is, so we have 10 millimeters thickness of the air and pressure 1. So we do go in calculate, and now we see down here the results is that the transmission now is almost 10%. So now we have a reasonable number of X-rays that can go through this air, and so we can expect to have indeed a good measurement of magnesium.